Now, redundancy and recovery, this is something we've been asked by customers, and this is something a section we've added as compared to the previous webinar from the summer of this year. So the system, basically, it keeps running if any of these current sharing cables are disconnected. There's a reason for them to be there, of course. It makes sure that every unit is providing the same amount of power, so there's no disbalance, but your system won't shut down if you disconnect these cables. So it's just one fault tolerance. PV might fail on any of the units because of a high PV voltage. It might be very cold, so the PV voltage might be higher than normal. The MPPT might be overheated completely, which is extremely unlikely because if it starts getting too warm, it will simply derate a little bit. But hypothetically, if it were overheated, then at some point PV would have to shut off. Or if you have any other fault on the PV side, then that will not affect your system, apart from the fact that, of course, you will be missing 1/5 of, in this example, 1/5 of your PV power. But it won't affect your AC side at all. Your system will keep running with 4/5 of the capacity, so basically you lose one unit in these cases. If your digital communication cable is disconnected, because we need that to talk between the units to make sure they're synchronized, etc. So obviously we can't send out AC current if we can't communicate, because if we're not correctly synchronized, that could cause a lot of damage. So then of course we turn off that one unit. Or if for some reason a microcontroller were hypothetically to fail in one of the units, or if we have a temporary shutdown of an inverter due to temperature or some other issue, then the system will just keep chugging along with 4/5 of the output capacity. And really the only cases where a manual intervention is required because the system needs to shut down, it needs to shut down typically because of security reasons or because it's just technically not possible to continue to operate, is when the parallel digital communication cables are short-circuited, so they literally have a short, because that means that none of the units can communicate with each other. Or if your AC output is internally short-circuited or externally short-circuited somewhere, then of course if all units are on the same phase, then they're all providing power to the same short circuit, so that's not going to work. If you do have a short circuit on the AC output, then the units will try to deliver power again every 10 seconds for 3 times before shutting down and waiting for somebody to come along to remove that short circuit. And during that attempt, they never provide more than 30 volts on the AC output side to see if the short circuit is still there or not. Now for system sizing, on the battery side, again, we are compatible with PylonTech batteries. You will need a specific cable, so please contact us for that cable to communicate with those units. If you're using any other battery, then make sure that you respect these charge and discharge currents that the various models require. If you cannot, because your battery is too small or is not capable of delivering that much current, then again, I mentioned before, you can reduce the charging current, and to a certain extent, you can also reduce the discharging current by simply temporarily switching over to the grid if you're using a battery which is essentially too small. For the PV array, I don't have time to go into all of these different various combinations, but suffice to say, as I've said before, you only ever need 1 or 2 strings per inverter to be able to take advantage of pretty much the full PV capacity. And the rules for setting up the PV array is that you must exceed the minimum PV voltage. So the minimum PV voltage is typically around 90 to 120 volts, depending on the model. And you may not exceed the maximum PV voltage. Obviously, that's why it's a maximum. So as long as you stay between those voltages, and you don't have more than 18 amps on the PV side, which you certainly won't with a single string, and with 2 strings, you're going to be roughly around 18 amps, then you're fine. Even if you're above that, it's okay. We can just use 18 amps as a maximum. If you're using an AC generator, we have various technical requirements that we recommend just to make sure that they work well together. We can work with, let's say, very dirty sine waves, very deformed sine waves. So typically this shouldn't be an issue even if you're using an inverter which doesn't quite meet these specs. Sorry, a AC generator. Now grounding and protection. This is a class 2 device, which means grounding is mandatory. So we have two grounding connectors, one for the AC input, one for the AC output. They are internally connected to each other. And this is a requirement for a safe operation that you connect to an adequate ground. Then there's the AC output grounding. Typically, you'll have an RCD, a residual current device, also called a GFCI in the Americas, which will monitor the current on all the lines. And if ever any current escapes towards ground, in other words, for example, somebody's touching a cable or there's a problem in any of the connected loads, then the RCD will cut power to all of these lines. Now, this RCD, I don't have time to go into the details, but it will only function if you have, at some point, you have a bridge between the neutral and ground. And you will have that if you're working with a public utility. But if you're working in off-grid mode, well, this section is completely disconnected, as you may remember. So in that case, you saw that in the topology earlier, the inverter, when it's in off-grid mode, it automatically makes this bridge internally. And that's just to ensure that your RCD or GFCI is working even in off-grid mode. For DC grounding, for the battery, you're very flexible. You can ground either the positive or negative terminal if you want. You certainly don't need to. We certainly don't prescribe it. It might be required in your country or by the battery manufacturer. And for the PV side, you may only ground the frame. You may not ground the positive or negative. The battery is the part that's galvanically isolated from the inverter and PV side. Then for surge protection, we give you some recommendations on what we recommend for the surge protective devices on the AC side. So please do install one, especially if your grid swings a bit. I mean, these are only for surges. So it's very relevant for, well, the Americas, where you have a lot of power lines which are above the ground. In Europe, it's a little bit less of an issue because most of it is below ground. But Australia, for example, has a lot of overhead lines, and they're just that much more susceptible to surges in case of lightning or thunderstorms. Surge protection on the PV side, again, we make a recommendation here. I'll update that. This recommendation is for the 230 volt models. We'll make a different recommendation for the 120 volt models. You'll actually see that later in the slides as well. And this, again, this is to avoid, like in case of thunderstorm or lightning, that we might have a surge on the PV side, and it's a good idea to have an external surge protective device to get rid of that overvoltage before it enters the unit. In the unit, we do have a limited surge protection as well, but it's not as powerful as having an external one, so we strongly recommend having an external one. Now for some system wiring examples. This will give you a lot of different examples which you can use as a reference to look up to make sure you don't forget anything when you're sizing a system. So for now, I'm just going to be looking at the 3 kilowatt units and the 5 kilowatt 230 volt units. I have a separate example for the 5 kilowatt 120 volt AC unit, because with the 2 MPP trackers, of course, we will have 2 PV arrays per inverter, and that will change things a little bit. So this applies to these 3 models. So we'll start off with a single unit. Again, this is like a best case scenario. You don't need to have a breaker on both positive and negative of the battery. You don't, depending on your country, it's not necessarily strictly required to maybe have a breaker on the PV side, but this is just a general recommendation. If you can do it, it would be great. And if it, if it saves the system in case of thunderstorm, well, that's a bunch of money that you can save in the long run. Because these breakers are not very expensive. We're looking at breakers which will cost $10 to $20 roughly. The RCD will cost maybe 40, 50. And the PV breaker also maybe 50. And the surge protective devices will cost another 30 to 50, roughly. So here in this matrix, you can see what the recommended values are for all these components. If we scale this up to a 5-unit system in parallel, again, you can, all these are labeled 1, 2, 3, 4, 5, etc. So you can just look them up in the table and immediately find the values that that these breakers or various devices need to be compatible with. Here we have 9 units in parallel. There's also a limitation for a lot of our competition to not have more than 3 units, for example, on a single phase. Like I said before, we can hook up 9 units together, synchronized, and we can literally put them all on a single phase. We're completely free to distribute those 3 units on 3 phases, on a single phase, or in a split phase configuration if you're working with the 120 volt models. Here we have the smallest size of a 3-phase system. You will need 1 inverter per phase, at least. And of course, you can then expand. You can have more than 1 inverter per phase. And this is the full 9 units symmetrically with 3 units per phase. So this is, if you're using a 5 kilowatt inverter, this will provide you with a full 45 kilowatts of AC power and about 43.2 kilowatts of PV power. So we're starting to get into quite interesting system sizes. And now finally, we have the wiring example for the PSW-H 5 kilowatt 120 volt unit. That's the one with the 2 MPP trackers. This also applies to the other 120 volt unit, the 3 kilowatt unit, which we'll be releasing in January. But for the 3 kilowatt unit, because it has only 1 MPP tracker, of course, just ignore the second PV array. The rest is identical. And what we're showing here is the split phase configuration, which I think will be of particular interest to the Americas, which are using 115, 120, or 127 volts. So in this case, we have a split phase system where we have 1 neutral, we have a 120 volt phase and another opposite 120 volt phase. So these are 180 degrees apart. And then of course, between phase 1 and 2, you would have 240 volts. So you can use on your AC output, you can use 120 volt or 240 volt loads, as is typical in, well, in those parts of the Americas where you have 120 volts. An important note, when you're using any of these PSW-H any grids, you must always have 1 neutral connected on the AC input if you are using the AC input. So you cannot use phase 1 and phase 2 on the AC input. You must always use a neutral plus a phase on the AC input. If you want to use the 2 phases, then I'll show you in a moment how you can do that with autotransformers or isolating transformers to get around that limitation. And that is also our final section for today, because we only have another 4 minutes. And then of course, I'll take the time to answer your questions at the end of the session. So I said before, if you have 2 phases, for example, on your AC input, then you cannot connect those directly to the any grid. You might also have scenarios where you want to convert between one voltage and the other. And that is, in a lot of cases, that's where autotransformers come in. Now, an autotransformer, auto means self, not car in this context. And it basically means that you have a transformer with a single winding. A lot of transformers are isolating transformers where you have 2 windings. In this one, you have a single winding. And that gives you no galvanic isolation, which in many of these examples we don't need. So that's a drawback we can live with. But it has two great advantages, which is first, that they tend to be a lot cheaper because there's a lot less windings, a lot less copper involved in these units. And on top of it, they are more efficient than an equivalent isolating transformer with two windings. So that's a rare combination in life, that something is more efficient and cheaper. So of course, we're going to want to use, if we need a transformer, we're going to try to use an autotransformer where we can, as compared to a classic isolating transformer, because we can save some money and even have a higher level of efficiency. So here are three use cases when we can use such an autotransformer. The first one might be we have a 120 volt AC source. And all of these autotransformers will not solve your problem that you are not allowed to have two phases connect to a single inverter. We'll see that's later for the isolating transformers, which will deal with that. So we're dealing with a 120 volt AC source with a neutral and a phase. And we want to power 240 volt AC loads. So of course there's a 2-to-1 conversion taking place. So we need an autotransformer which can convert the lower voltage to the higher voltage. So a ratio of 1 to 2. Now you can use that ratio of 1 to 2 with a 120 volt PSW-H transformer by putting the transformer between the inverter and your loads. So basically on the AC output side. Or you can use that same autotransformer and use a 240 volt PSW-H, which is going to be a little bit cheaper per watt. And then instead of using it on the AC output side, you put it on the AC input side between the AC source and the inverter itself. And you can do the opposite of that. I don't need to go through each line because we're running out of time, but it's exactly the same story, just the opposite. Now we have a higher AC input voltage and we want to convert that to half the voltage. So we have a 2-to-1 autotransformer and pretty much the same story on the other side. And then we might have a non-split phase AC source, 120 volts and 240 volt loads, where again we can use a 2-to-1 autotransformer. And what this looks like is, for one of these examples at least, to give you an idea, if we have a single phase AC source, so a single phase 240 volt, but we have both 120 and 240 volt loads, then we can use an autotransformer in this scenario because we have a neutral on the AC input as required, and we have a neutral on the AC output, of course, too, and we can just pipe some of the power directly through the autotransformer as if it weren't there, and then we can also convert that to half the voltage by taking the middle of the winding, basically, of this autotransformer. And to finish up, we have the isolating transformer as well. And really the only time we need that is if we're working with split phase and we only want to use a single inverter. Normally, if we're working with split phase, you would need two 120 volt any grids. But in some cases, that might be too expensive, or you might not have such a high power requirement. So in those cases, you can use a single inverter, but you will need an isolating transformer then to deal with the neutral thing. Remember that we may not connect two phases to a single inverter. It must always be a neutral and a phase. So that's what this last example shows. Now we have an isolating transformer. Now we have two windings as opposed to the single winding on the autotransformer. And between that, we have our isolation. So now we're isolated from the grid, and that means we can rearrange the neutral as we like. And if we arrange it this way, this is actually a great example, which I didn't come up with, that our team in Germany came up with, where you can get away with using an isolating transformer with only half the nominal power. So typically in a scenario like this, you would need a 5 kilowatt inverter if you're using a 5 kilowatt transformer, or if you're using a 5 kilowatt inverter. But if you're going to use this type of wiring, then you can actually get away with a 2.5 kilowatt inverter, transformer. because you're only really converting half the power. The rest is just flowing straight through. So this, although you're going to need a more expensive isolating transformer as compared to an autotransformer, we only need half the power. So that kind of offsets that difference to a certain extent. So I know that was a lot of material towards the end now, which is quite technical. Again, everything is on the slides, so you can look that up later. Okay, thank you very much, and have a good day.
For more videos and information, go to www.phocos.com. Phocos, making reliable energy access possible. Anywhere, anytime, any grid.